Thank you very much for a kind introduction. For 3 terms, I served as the selection committee member for Kyoto Prize, and therefore it's a great honor for me to be invited as a speaker to this symposium. I would like to talk about the creation of mathematics. I would like to describe how mathematics is created based on purely on my the personal experiences. Unlike other fields, the mathematics is a field. To describe it is quite difficult. It's quite difficult to try to explain what we are trying to do in mathematics. I would have to use some special terms, mathematical terms, but you don't need to be worried. Just try to get the feeling of what we are doing. Hope this assumption will be accepted, because I've already decided what I'm going to say, so it's meaningless to try to get your understanding at this moment. I would like to talk about resemblance, and through the resemblance, I think it's possible to connect 2 different fields. This is one of the way how mathematics is created. You can see the Euler's formula, exponential function, and the trigonometric functions are connected. And Professor Feynman said this is our dual. But these 2 exponential function comes from the need to simplify the numerical calculation, and the trigonometric function comes from the trigonometry necessary to measure the land. And these 2 completely different functions from different origins are now connected in the world of complex number. Today, I would like to try to connect 2 different fields through the eyes of analogy or resemblance. This is the contents of my presentation. I would like to focus on 5 aspects, or 4, because I may not have time to talk about the last item, another application. First of all, I would like to talk about Dirichlet's theorem for arithmetic progression. It's deeply related to the study of prime numbers. Prime numbers have been the object of interest of mathematicians from ancient Greek or much earlier, since the time of Euclid. So these are the special numbers, the special numbers. And there has been various results on the distribution of primes have been obtained. You can see the name of the mathematician who contributed to the theory of prime numbers: Euclid, Eratosthenes, Feldman, Euler, Lagrange, Gauss, and Dirichlet, and Riemann. And the list continues. Famous mathematicians have contributed to this field. Purely because of interest, the study on prime numbers started. But today, for encryption, primes are quite important as part of the public key. So the turn of events for the study of prime number is quite surprising. First of all, I would like to talk about the Dirichlet's theorem of arithmetic progression. Then I would like to talk about the analog. This is Euclid. Of course, this is not a picture, so there is no way to prove that this is actually Euclid. In the element, Euclid stated as follows: there are infinitely many primes. He expressed in a different way, but his message was that there are infinitely many primes. These primes, the number of primes are infinite. And the prime factorization is quite important because any positive integer is uniquely expressed as a product of primes. And it's easily proven. You can see 4 and 8 and 10, all of these are expressed as a product of primes. After many centuries, the Fermat, he is a pioneer of modern number theory. And the Fermat's the last theorem is quite important. And perhaps Diophantus gave influence to Fermat, and this is Fermat. And this is a proposition he demonstrated. Every prime p of the form 4k plus 1 is expressed as p equals a squares plus b squares with some positive integers a and b. So certain special primes are expressed as the sum of two squares, like 5, 13. 13 equals 2 squares plus 3 squares. But the question is, are there infinitely many primes of the form 4k plus 1? There are infinite number of primes, but are there infinitely many primes of this particular form? The answer is yes. And it's generalized in the following way. This is what Dirichlet proved. If A and B are co-prime, then there exist infinitely many primes of the form of AK plus B. Fermat's primes are in the case when A is 4 and B is 1. 4 and 1 are co-prime. This is Dirichlet. I will explain one notation. This is commonly used one. We denote by GCD-AB. This means the greatest common divisor of A and B. GCD-AB. When it's 1, this means A and B are co-primes. Next, another notation. We denote by RAN the remainder when a positive integer n is divided by a. RAN remainder is 0 or above 0 and less than a. R1537 is 7. 37 divided by 15. The remainder is 7. And this is a paraphrase of Dirichlet's proposition. B is 1 or above 1 or less than A, and GCD-AB is 1. Then there exists infinitely many P with RAP equals B. What is the advantage of this way of expression? Think about the following sets and GA, B, 1 or above 1 and less than A, and GCD-AB equals 1, and GA is a set of B satisfying those conditions. And the phi A expresses the number of elements in that particular set. This is what we call Euler function. If we denote by large P the set of primes, then RA gives a map of P into GA. I don't want to use the term map, where map can be expressed as a function of P into GA. G3. The set has elements of 1 and 2. And G4 has elements of 1 and 3. They have only 2 elements. And GA is not a simple finite set. GA has an operation. The new multiplication M circle n in GA is defined to be the remainder of Mn when divided by A. So this is how we define M circle n. And they form a group. But before talking about the group, think about a case A equals 12. G12 has elements of 1, 5, 7, 11. And this is the result of the new multiplication. And if A is 15, and these are the results of the new multiplication. Important thing is that the GA is an abelian group with respect to the product M circle n. And the associative law must be satisfied, and existence of the identity element is required in the set. And thirdly, for any M which is an element of GA, there exists N which is an element of GA such that the M circle n equals 1. Existence of inverse elements are required. When 1, 2, 3 are simultaneously satisfied, those sets or those algebraic systems are called a group. And in the case of GA, M circle n equals N circle M, so the commutativity is satisfied. And when this is all satisfied, the groups are called abelian group. And you hear a lot of groups in the contemporary mathematics.
This is the density theorem. This is based upon Dirichlet's AK plus B's, where with the infinite primes, then his theorem was refined to have the density theorem. Pi x equals, that is the number of primes less than x. Pi x AB, this is the number of the remainders when P is divided by A. This is again the number of primes, and that is the pi x AB. So as shown in the Dirichlet's theorem, the primes AK plus B, in order to count them, this can be used. And with the pi x and the pi x AB is divided by pi x, so in all the primes, the AK plus B's, how many of them exist? This is to consider the percentage when the x approaches infinite, and then we have the radicals of the Euler functions. This is irrelevant from the number of b. And when the b is moved, still the ratio remains the same. To prove this theorem, the zeta function or L function becomes necessary when A is equal 4 in the case of Fermat, and then the G4 is 1, 2, 3. And in other way of writing is when the G is 1, and then the prime number 4k plus 1, the number of that primes are counted. If it is 3, and again the primes are counted, and the ratios is always the half. So the number of primes in these forms exist in the same ratio. Going back slightly, the Euler introduced the zeta function to study primes, which is quite simple. The 1 and 2 and 3 and going on is added with the negative power. And then we can use the prime factorization. And then we have this formula. This is a product formula. And by using this zeta functions, the Euler proved this again. Since the zeta s diverges at s equal 1, there exist infinite many primes. So there is an infinite number of primes. If there is only finite number of primes, and then the product formula should become different. Then what the Dirichlet proved? He employed the following function as a generalization of the zeta function in order to prove his theorem. The denominator used to be 1 in the zeta function, but now n is placed instead to get the summation. Here, chi this is called the characters of Dirichlet, but this has the nature of that. And again, there is the product. And the L function, by using this nature of L function, the primes of AK plus B exist in an infinite number, he proved. And after that, the Riemann proved that the zeta function, then the L function, is extended to S in C as a meromorphic function. By using this, this is a Riemann portrait, and then Adamar and Poussin in 1896 separately came up with the idea of a prime number theorem. The pi x is similar to x over log x as x approaches infinite. And so pi x divided by this becomes closer to 1. This is very rough, but this describes the pi x nature with the already well-known functions. And the prime number theorem for arithmetic progressions can be described as follows. Knowing this, and then if we know the density theorem, then we can come up with this. By extending it to complex number, we can get it. And you may know Riemann hypothesis. This is considered to be the biggest unsolvable problem in the 21st century. And the zeta function is extended to the complex number, and then the points zeros are the real part, and it is on the line of 1/2. Riemann checked 3 or 4 cases only, but after that, this imaginary part, from the smallest one up to 10 trillionth, all the complex zeros are on this line, so it should be right. But 10 trillion versus infinite, the ratio is 0, so this is not strong enough yet, but the probability is very high. if this Riemann hypothesis is true, and then these asymptotic formula can be described in more detailed ways. The prime number theorem and the prime number theorem have been mentioned, and the analog of this can be generalized to the case of prime ideals of a number field. So just briefly I'll mention about this. This is going to be the toughest part, so please be prepared. Generally speaking, we call something a field, and a field is an algebraic system of numbers on which four arithmetic operations can be performed. And the rational numbers, the fractions, are also part of fields. And a field large K is called an extension field of a field small k if the small k is a subset of large K. We write as is written here. Once the extension field is given, and then Galois group will be given too. I don't like to detail about this, but a large K over small k, if it is given, and then the group will be corresponding to that. How to define it is written here, but do not worry about this. But this is actually very important to understand. In the extended form, the Galois extension, which has a very good nature, and this is almost a spell, but the Galois group, if the Galois group is Abel group, and then the large K over small k is called an Abelian extension. And then number fields. The rational number fields can be generalized a little bit. It is the field with the addition of algebraic numbers, and the rational number with alpha, and the Q alpha is how it is written. And it can be described as K equal the rational A. Q alpha is an extension form. And then where alpha is said to be an algebraic number if it is a solution of algebraic equation with rational coefficients, it says. And just one example, exponential in Euler's formula. And then x to the power of a equal 1, and then its solution is zeta alpha equal to exponential, and the firstly introduced Abel groups GA is equal to this. This is called the cyclotomic field. In the number field, this is a representative field. In the case of Q, in the rational numbers, the primes will be considered, but in general, number fields, the more generalized, the prime ideals, and we can introduce the notion of ideal and prime ideals as a generalization of positive integers and prime numbers. Or it is the analogues. I needed to explain detailed definition, but I would rather spare with it. And large K over small k, is the average extension of number field small k, and the k's prime ideals set is considered to be sub k, and then that constitute the map of Galois groups. And the map I mentioned the Abel extension, and then this is the Galois group of cyclotomic field, and it is a little bit generalized mapping here. And what I want to do here is that P to G k over k, when prime number is divided by A, and by the remainders that prime numbers were grouped. But here the Galois group with the Abelian extension, by using it, the prime ideals are being categorized. And in this categorization, how many prime ideals exist? And the prime theorem, or the analogues and the generalization can be used here. And so the generalization of the prime number theorem and arithmetic progressions can be proved by this. And then there are cases not abelian groups. There are another method to do the same. But I don't mention about that in details. And what are we going to use? And that is the generalization of zeta function of Dedekind. The NP is norm of P. The positive integer determined by prime ideals. And the generalization of prime ideals, the L functions generalization will be considered by using these natures. These two theorems are proved. This is something to remember. This the field small k and extended large K, and generally Galois group and the Abel group's case is especially important. And then the rational number and the cyclotomic field, and then the corresponding Galois group is A, and then these two are analogous. Next, please switch. Let me switch gear a little bit. That is about the dynamic system, the analog of Dirichlet theorem for arithmetic progressions. I have handled number theoretic objects, but now let us think about a geometric analog. And a dynamical system is a system whose state evolves with time over a state space according to a fixed rule. The dynamical system is defined to be a pair of a set X and a family of maps of the Ft with time parameter t satisfying. When t is 0, this should be P, and at the time t, and then this S lapse, and then that will be the value to S plus T. This is how I can use the schematics. This is called orbit. And some orbit comes back to the original state. This is called a periodic orbit. The period of the periodic orbit is denoted by LP. And the periodic orbits is considered to be analogous of primes, and we count them with their period.
We need to convince people that the periodic orbit is analog of primes. And at the beginning, I was not convinced, but here is the background analogy between the dynamical system theory and the number theory. Dynamical system, a number field, covering map, field extension, and covering transformation, a Galois group, and periodic orbit sets, the prime ideals sets, homology group, with the Galois group or maximal abelian extension of K and the homology's correspondence. In the context of dynamical system, an analog of class field theory holds. However, a big difference is that the homology group may be an infinite group. According to the classical class field theory, may be different from the contemporary method. The classical theory dealt with only the finite groups. However, in contemporary mathematics, we have to think about the infinite groups. This is about covering maps. It's really about covering. This is a straight line made into a chord. When you see it from above, when you get a map, there is a circle as if it's covering. As Professor Modi was talking about, if you have a plane, then if you have a covering map, it's expressed as a torus. The red points and the blue points are covering onto a torus. And this is analog to the extension field. K to K map was a set. In the case of field extension, in the case of the covering transformation, there are two roots which results in the same consequence. And this is analog Galois group. What about homology? Homology is used in order to classify closed curves. Closed curves on a surface are classified as follows. There is one closed curve. According to this line, you cut it. Then there would be two surfaces. Therefore, the homology class is 0. On this case, again, if you cut it here, then the surface is not divided into two. Therefore, the class is unequal to 0. So this is the homology and how it's defined. And the prime orbit theorem. This is an analogy of prime number theorem. Let Ft be an anosov dynamical system. And I don't have time to give a detailed explanation. Suppose there is a vertically long rectangle. Over time, it transforms into horizontally long rectangle. And this change takes place at all states in this closed dynamical system. Even if you have a similar the initial condition, over time the chaotic state occurs. Therefore, this is a very unstable system. Pi x is defined as the number of the p when Lp is below x. Then there exists a positive number larger than 0. And this is exactly same as the prime theorem. H is what we call the topological entropy. Margulis and Perry-Policot independently proved this proposition. In 1990, if you have one the homology class, then if you do the counting like this, and if B is defined, you need to have this term because generally homology class is infinite. But it's possible to express this in the dynamical system. And we use an analog of L function. They are quite similar to each other. There are some only small differences. And lastly, I would like to talk about the Kroneker's the Jugendtraum, or the dream during the youth. This is about the equation. I think you know the quadratic equation, which can be solved by using radicals. And Tartaglia and Ferrari separately proved that the cubic and the quadratic equation can be solved by using radicals. But in 1824, Abel proved that it's impossible to solve the general polynomial equation of the fifth degree in terms of radicals. He studied a class of equations, which is now called abelian equations. Then Galois made a correspondence between polynomial equation and field extension, and he said that one can decide whether an equation has a solution formula in terms of the structure of the Galois group. An abelian equation is a polynomial equation whose Galois group is commutative. Abelian extension is quite important. Using the class field theory, one can investigate all abelian extension of a given number field K in a logical way. We have to be careful. I said that you can investigate logically, but it's not about a concrete way. And the Kroneker's dreams is about constructing an abelian extension of a given number field in a concrete way by using a transcendental function and algebraic geometry. So this is the Kroneker. Kroneker proved together with Weber in a case of cyclotomic field. Every abelian extension of the rational number Q is a subfield of a cyclotomic field. The Kroneker's original dream is the case of an imaginary quadratic field. And this special case was solved by Dr. Takagi. However, Kroneker's Jugendtraum in the general case is still unsettled. There is a big difference between showing the existence of a mathematical object in a logical way and constructing a mathematical object in a concrete way.
This is just one example I'm going to show you. There exist irrational numbers a, b, such that a to the power of b is rational. And Jardin proved as follows. Root 2 is irrational. Everybody knows if you studied at high school. And if root 2 to the power of root 2 is rational, then it suffices to put a equal to b equal to root 2. And if it is irrational, root 2 to the power of root 2 is irrational, and then it suffices to put an a equal root 2 to the power of root 2 and b equal root 2. And by using the exponential natures, it becomes eventually 2. So in either case, the rational numbers can be obtained, and then this is proved. Looking at this, you may understand it is cheating a little bit. Logically, it's okay, but we don't know whether it is the rational or irrational, but we did it definitely anyway. But this proof never gives A or B in concrete forms. The root 2 to the power of root 2. And then A is as such and B is as such. But just looking at this proof, the concrete the proof is not given. So the Kroneker's dream, and in logical terms, the class field the theory have been proved, but in concrete way there is no explanation about this. And then this is related to the geometric analog of Kroneker's dream and design of crystal structures. Crystal is the special form of the graph. This is the finite graph examples. The crystal structure is A dash, B dash, and C dash. In the natural world, A dash and C dash exist. This is rose daylight, and this is diamond. There are an idea to describe this in a graph. This consists of the side, vertex, and edge. And then the graph theory has the analogous nature with the number theory. And also zeta, the function, also has an analog. So we consider the abelian covering graph. We can think about that. And then the abelian covering graph of a finite graph is called topographical crystal. This can be described as living in the logical world, not in space, leading to the question of how to place or realize it in space in a concrete way. We can utilize the discrete algebraic geometry to realize the given topographical crystal in space. This was proven in 2012. This is a graphic version of the Abel extension with the Abel covering. And then we use the discrete algebraic geometry. So this is a geometric version of Kroneker's dream, if I insist. And this realization minimizes a certain energy and has the maximal symmetry. So let's skip this. There are many examples of standard realization. Two-dimensional lattice, and also the three-dimensional diamond crystal, and Lon's daylight crystal. Now it's time, so the negative answer to Kat's question, can one hear the shape of a drum? I'll just run through the slides. Thank you very much. This was the power of an analogy. Thank you for your attention.